In sections 2.2 to 2.4, we're going to be focusing on using the first and second derivative tests and curve sketching. So we have looked at properties of our graphs before with increasing and decreasing and concave up and concave down. So now we're going to find that we can find these properties based on our first and second derivative, respectively. So these relationships will provide the key to curve sketching and optimization. So how do we do this? Our general approach says we start with our given function f of x, and we find f prime of x and f double prime of x. Then we're going to locate all relative maximum and minimum points and make a partial sketch. So this is where we're finding, remember they're called critical points. So where we find our critical points and we can make a partial sketch. Then we're going to find all of our inflection points in our concavity. And we're going to then be able to incorporate the concavity with the maxes and mins. And along with our maxes and mins, not only are we finding critical points, we're also going to be finding where the function is increasing and decreasing. This will help us begin to shape our curve, because if we have increasing and then decreasing, we know we have a max. And if we have decreasing, switching to increasing, we know we have a min. And then if we add concavity, where we know it looks like this, we know then that our shape of our graph starts to look like this. So the question is really, where do we begin? Well, we begin by looking for those critical points by setting our first derivative equal to 0. And if you remember, we talked about this in class because we said where we have a maximum, we have a slope of our tangent line is 0. Where we have a min, the slope of our tangent line is also 0. And remember that f prime of x is the slope of the tangent line. So what we're really looking for is where is f prime of x equal to 0. So that's why we look at it. And our first derivative rule says that if f prime of our point is positive, then our function is increasing there. And if f prime of a point is negative, then our function is decreasing there. So that makes sense too, because if you think about our examples up here, if I were to look at the slope of my tangent line over here, that slope is negative, and my function is decreasing. Whereas, and the same, if I looked on the left-hand side of this one, I have a negative slope, and I have my function is decreasing again. However, if I were to switch to the opposite sides here and did a tangent line, then I have a positive slope and my function is increasing. Likewise over here, I'd have a positive slope and my function is increasing. And that's all this first derivative rule is saying, just with some pictures from the textbook. Let's see if we can start putting some of these concepts into action with an example. So example 1 says, sketch the graph of a function that has the properties described. F of -1 is 0. F prime of x is less than 0, aka negative. For x less than -1, f prime of -1 is 0. Oh, that makes this a critical point at x equals -1. So it's a possible max or min. Right, we'll figure out which. And then we have f prime of x, our derivative is positive, greater than 0, so this is positive, for x greater than 1. So where our function is negative, or sorry, our derivative is negative, our function, f of x, is decreasing. And then we also know where our derivative is positive, that means that our function, f of x, is increasing. So if we were to take all of this information and put it on one number line that represents our derivative. So this is our derivative number line, f prime of x. We're going to just ignore for the moment, this f of -1 equaling 0. We'll come back to it because we will need it, but for now, let's just focus on the derivative. Well, we know that our derivative is negative when x is less than -1. So it's negative down in here, which means our function is decreasing. It has a negative slope. We know it's 0 at -1, so that's a possible max or min. And then we know it's positive when x is greater than -1, which is an increasing. So this is our increasing f of x, and this is our decreasing f of x. So we have a function that is decreasing and then turns to increasing. So you can see just based on the shape here that this is going to be a minimum. So what might that look like on a graph? Well, it just means we know we have the point f of -1 is 0. What our first derivative is telling us is that our function is decreasing all the way to that -1, and it's increasing all the way after. So what that likely looks like is something like this. It looks like a quadratic. So how can the first derivative test help us find local extrema? Well, we saw in the last one where a function went from decreasing to increasing, we had a minimum. So that was, looking here, that's B. That's where we say if f prime changes from negative to positive at x equals a, then f has a local minimum at a. So that was when we looked at our f prime of x number line, and at a, for us in our last example was -1, we had decreasing to increasing. That gives us a min. When we flip that around, that's a up here. That says, well, what happens then if my first derivative at a switches from increasing to decreasing? Well, we can see that that gives us a peak, so that would be a max. The only other option we didn't really look at was what happens if it's the same sign on both sides of a. So perhaps f prime of x has a number line that looks like this, where it's negative, and then it's still negative. So it's decreasing, and then it stops, and then it's decreasing again. Well, that might come from a function that maybe isn't continuous everywhere. Maybe it's always decreasing. So if we looked at 1 over x, it's always getting smaller, and then it has a jump at 0, and then it's still always getting smaller. This is f of x equaling 1 over x. It's a rational function. So it has an undefined slope of a tangent line at a. We mentioned this at the very end of section 2.1. Has an undefined slope at a. So this is one of those special cases. We may also find that f prime of x could be a positive. So at a, it might be increasing and then continuing to increase. Well, that might look like a function that says, okay, I'm going to come up, sort of level out, and then continue on. So you can't really call this point either a minimum or a maximum. It's neither. It just levels out instantaneously at a and then continues on. But it's always increasing. Let's see if we can do one example all the way through with just our first derivative test. So with this example, I said, let's find the extrema for the function f of x equals 6x cubed plus 3x squared minus 3x plus 3. So first steps first, we always find the first derivative. So let's find f prime of x, which would be 18x squared plus 6x and minus 3. Then we want to set it equal to 0. So 0 equals 18x squared plus 6x and minus 3. In this case, This one is not factorable, so I'm going to use the quadratic. I'm going to use the quadratic formula to solve for x. So here, x would be negative b, so negative 6, plus or minus the square root of b squared, so 6 squared, minus 4 times a, which is 18, times c, which is negative 3, all over 2 times a, which is 18. Oops, I think I wrote an extra one there. There we go. 2 times 18. So we're seeing how some of that review material from chapter 0 is coming back again. So we end up with x equals negative 6 plus or minus the square root of 252 all over 36, which is negative 6 plus or minus 6 root 7 over 36, or when we simplify it down by pulling out a 6 on the top, negative 1 plus or minus root 7 all over 6. And this is equal to, in decimals, 0.274 approximately, and negative 0.608 approximately. So we know where to put them on our number line. We'll kind of be able to tell what it looks like. So let's look at that number line. We have f prime of x, and here's our number line. I didn't make that very straight. Let me try it again. Here we go. There's our number line. It's as close as it's going to get to being straight. Negative 0.608 is definitely less than 0.274. So on our number line, remember, we're still increasing, going from left to right. So still negative infinity to infinity. Still the same number line you're used to seeing, right? So what we have to do now is we need to find some points that lie here in this interval, and here in this interval, and here in this interval, to test to see whether our function is increasing or decreasing. So what I'm going to suggest is that maybe we test negative 1. So if we test negative 1, let's see what f prime of negative 1 looks like. Well, that would be 18 times negative 1 squared plus 6 times negative 1 and minus 3, which is 18 minus 6 minus 3. So 18 minus 9 is 9. That means my function is increasing over that interval. For the middle interval, from negative 0.608 here to positive 0.274, anytime you change from a negative to a positive, you've passed through 0. So the easiest number to plug in is 0. So we're going to test 0. So let's find f of 0, or f prime of 0. So f prime of 0 would be 18 times 0 squared plus 6 times 0 and minus 3, or it's just going to be negative 3. So our function is decreasing between our two critical points. And lastly, we need to pick a value that's greater than 0.274 but less than infinity. So we're going to pick, let's just keep it easy, let's pick 1. So let's find f prime of 1, which would be 18 times 1 squared plus 6 times 1 and minus 3, or 18 plus 6 minus 3, or 21. So it is positive in this interval, so our function is increasing. So if we were to go through and label what's happening here, f of x is increasing, f of x here is decreasing, and f of x here is increasing again. So we have increasing, stopping at a peak, and then decreasing. So that sounds like a maximum to me. And then from there, we see that once we start decreasing, we stop, turn around, and start increasing again. We have a trough there, or a valley. So that to me says min. And this is also what our first derivative test said on the last page. So we would have a maximum at x equals negative 0.608 and a minimum at x equals 0.274. If you're doing this on Pearson, they might ask for the radical versions down here instead. So they might want, instead they might want the -1 minus root 7 over 6 and -1 plus root 7 over 6. So they might want those instead. Just pay attention to what it says. Sometimes they'll allow you to approximate with a decimal, sometimes they won't. Just be really careful when you read the directions. Let's try another one. Pause and see if you can figure this one out on your own. You might be surprised that it's a little different than you expected when you do your first derivative number line. All right, now that you've had a chance to try it, let's look at our first derivative. Our first derivative, f prime of x, requires us to use our chain rule, right? Bring the 3 down, times 3x minus 1, drop one of the powers, 3 goes down to a 2, times the derivative of the inside is just 3. So we end up with 3 times 3 is 9, times 3x minus 1 quantity squared. And we're going to set this equal to 0. So here's the cool thing is that we can divide both sides by 9, and we still get 0 equals 3x minus 1 quantity squared. So the only way this can be 0 is if 3x minus 1 equals 0, or 3x equals 1 if we add 1 to both sides, and then divide through by 3, we end up with x equals 1/3. So x equaling 1/3 is our only critical point. So let's look what our f prime of x graph looks like with 1/3 in the middle. We know that's where our derivative is 0. So now, knowing that we've got our negative infinity down here and our positive infinity up here, let's test some values around 1/3. Let's test maybe 0 here. Well, what's f prime of 0? Well, f prime of 0 is 9 times 3 times 0 minus 1 squared, or 9 times -1 squared, which is just 9, so it's positive. So our function is increasing from negative infinity to 0. Well, let's test another value to the right of 1/3, or greater than 1/3, so let's pick 1. Remember, stick with the easy values if you can. -1, 0, 1. And here we can, so let's find f prime of 1. We get 9 times 3 times 1 minus 1 quantity squared, which would be 9 times, well, 3 times 1 is 3, minus 1 is 2, so 9 times 2 squared, which would be 9 times 4, which is 36. Well, this is also positive. So we have a positive to a positive. So that means we don't have any max or min. So our function f of x is increasing, and then it must level off a little and then keep increasing. So therefore, we have no extrema. There are no maxes or mins. So this is likely one of those graphs that looks like this, where it just sort of levels off momentarily and then continues to increase. So much like we can find critical points by finding where the first derivative is equal to 0, we can also find inflection points by finding out where the second derivative is equal to 0. So our second derivative rule says that if f double prime of a is positive, then f is concave up. And if f double prime of a is negative, then f is concave down at x equals a. And remember that concave up is our smiling happiness, and then if concave down is our frowning. And then we have the second derivative test for local extreme points. So this builds on what we learned before. And it says if our first derivative is 0 and our second derivative is negative, aka concave down, right, then f has a local maximum. Well, that makes sense because that would be up here. And if our first derivative is 0 and our second derivative is positive, meaning concave up, then we have a local minimum. So again, not surprising because it would be at the bottom of our smile there. Here I've given you some pictures and a chart to help remind you of what all this means. So what does our second derivative rule say? It says that if f prime of a is positive, then f of x is increasing. And if f double prime of a is positive, our function is concave up. So this is our concave up, right? And it's increasing, right? It's going up and to the right. So if our first derivative is positive, our function is increasing, but our second derivative is negative, then our function is concave down. So you'll notice it's still increasing, but now it's curved in a different way. For our third example, we have a negative first derivative, meaning our function is decreasing. Makes sense. And this time it's curved more like a bowl that's open, so it's like a smile. That means it must be concave up, which is absolutely where our second derivative is positive. And the last example here is where we have both a decreasing function, because f prime of a is negative, and we also have a concave down function because f double prime of a is negative. So yes, still decreasing, but also concave down. So what does it look like when we put all of this together? So let's sketch our graph with the following properties. We know the points 2, 3, 4, 5, and 6, 7 are on our graph. We also know that our first derivative is 0 at both x equals 6 and x equals 2. We know that our second derivative is positive for any x less than 4. We know that it is 0 at 4, and we know that our second derivative is negative for any x greater than 4. So let's start first with looking at f prime of x and f double prime of x on number lines, where we can line them up. So we're going to draw them one under another. We know that we have critical points at both 2 and 6. We know that our function first derivative equals 0 there. So we know we have possible maxes and mins there. We weren't given any information about whether the function is increasing or decreasing on anywhere around the intervals around those two critical points. What we were told is that f prime of x is positive for any x less than 4. So let's drop in our 4. We know that our function is concave up anywhere where x is less than 4. And then we were also told it's 0 at 4. That's our inflection point. And then we know that it's negative anywhere greater than 4. So we can look at this and say, if I have an extreme point here, it's going to be at the bottom of that curve. And here it would be at the top of this curve. So that makes x equals 2 a minimum and x equal to 6 a local or relative max. Local or relative, right? So could we sketch this graph? Well, we actually could. Let's see here. If we did maybe 2, 4, 6, 8. How about that? And then we've got 2, 4, 6, 8 out here on our x. Well, let's plot our 3 points that we were given, 2, 3, 4, 5, and 6, 7. They kind of look like they make a straight line. However, now that we've got these guys in, we know that we have a minimum, a local minimum at 2, right? So we know it's going to bottom out at 2. It's going to change inflection at 4, and we're going to have a maximum at 6. We don't know exactly where it's going to cross the y-axis or the x-axis again, but we know that it will. So we have our minimum at x equals 2, we have our maximum at x equals 6, and we have our inflection point at x equals 4. I'd like you to pause and try this one on your own, and then come back to check your answers. So first things first, you need to find your derivative f prime of x, which is going to be 3x squared plus 12x plus 9. Then we're going to set it equal to 0. So 0 equals 3x squared plus 12x plus 9. We can factor out a 3, and we're left with x squared plus 4x plus 3. So we know then what multiplies to give me 3 and adds to give me 4 are plus 3 and plus 1. So when we set this equal to 0, we find out then x plus 3 could be 0, or x plus 1 could be 0. So x is either negative 3 or negative 1. So we're going to need to test f prime of x around these values. So here's negative 3 and here's negative 1. Remember, as your number line goes from left to right, that's negative infinity to positive infinity. Negative 3 is less than negative 1, so it needs to come first. So let's test maybe negative 4. If we were to plug in negative 4, we would get negative 4 plus 3 is going to be a negative 1. Negative 4 plus 1 is negative 3. So we're going to negative times a negative times a positive, which is going to give us a positive. If we were to plug in a value between negative 3 and negative 1, like say negative 2, we would get negative 2 plus 3 is a positive 1. Negative 2 plus 1 is a negative. Positive, positive, negative gives us a negative. And then likewise, we could just pick 0 out here. So when we plug it in, we're going to end up with positive, positive, positive. So it's going to be positive. So we can see that we're probably going to have a local max at x equals negative 3 and a local min at x equals negative 1. But to be certain, we're also going to find f double prime of x, right? Our second derivative, which would be 6x plus 12. We're going to set that equal to 0. So negative 12 equals 6x, so x equals negative 2. And we're going to plot that on a number line as well. So we only have one inflection point at negative 2. So once again, we need to plot some values around it. Something less than negative 2. Let's go with maybe negative 4. So 6 times negative 4 is negative 24, plus 12 is still negative. So we end up with a concave down. If we plugged in something greater than negative 2, like say 0, we get 12. So positive and concave up. This matches with what we thought because this implies a maximum and this implies a minimum, which is exactly what we found based on our increasing and decreasing. So what might our graph look like? Well, you can plug it into your calculator to double check what it looks like. But what we know is that we have the point negative 3, 0. Right, that's negative 3, 0. And that's going to be a maximum. We know this is going to be a max. We have the point negative 2, negative 2. Right? Negative 2, negative 2. That's going to be our inflection point. And we also have negative 1. Right? Negative 1, negative 4 is going to be our min. This is our, oops, sorry, I didn't label that negative 1, negative 4. So our graph is going to have a local max here, we concave down, and then switch to concave up, have a min, and then it's going to come back up, believe it or not, through 0, 0. Not that I drew this curved as well as I should have. Not the best artist, sorry. We've got our y-intercept here of 0, 0. So you can confirm all of this based on your calculator. Hit your y equals button, plug in the function, and you will see that all of this is true. So when you're working on curve sketching and you want to find your max and your min and you want to double check the graph, you can always put it into your fancy TI and double check that your graph matches what you think it should. Let's try another. So let's sketch the graph of fx equals x cubed minus x plus 2 without our calculators. So we start with, as usual, find f prime of x, which is 3x squared minus 1. Set it equal to 0. So 0 equals 3x squared minus 1. So 1 equals 3x squared. So 1/3 equals x squared. Take the square root of both sides or raise both sides to the 1/2 power, however you want to think about it. And you find out that x is plus or minus the root of 1/3. So now when we plot this on our number line, f prime of x, we're going to have negative root 1/3 and positive root 1/3. This is going to make substituting in points very easy because we can do -1, 0, and 1. Because remember, we're still doing negative infinity here, out to infinity here. So if we plug in -1 here, we end up with 3 times 1 minus 1, so it's positive. If we plug in 0, we get 3 times 0 is 0 minus 1, negative. Plug in a positive 1, we're also going to find that it's positive. So we can already see that we're going to have a possible max at the negative root 1/3 and a possible min at the positive root 1/3. Let's see if our second derivative agrees. So f double prime of x would be the derivative of 3x squared minus 1, which is just 6x. And we set that equal to 0, and that's just where x is 0. So let's see. When we look at our number line for f double prime of x, literally our only inflection point is 0. Still going from negative infinity to positive infinity. Test a -1 and a positive 1. 6 times -1 is -6, so we're negative and concave down here. And 6 times 1 is positive, so we're positive and concave up. Again, implying a maximum and a minimum. So absolutely, our second derivative agrees. So we could do the same thing as the last one, and we could find points to plot. But I'm just going to give you a general idea of what it looks like. So a general idea of this graph might be something that looks like this, right? Because at 0, we would have 2, right? This is 0, 2. Let's see, our min is at, this would end up being here. This would be the positive root of 1/3. Our max here, not that I drew it to scale, would be at the negative root 1/3. And we could plug those in and find out what those values are. But I didn't do that for this one. So I was just going to give you a general sketch on this one. We have one more where we're going to do another general sketch, and then we're going to summarize what we've learned. Okay, so for our last example, we're going to sketch the graph of f of x equals x cubed minus 6x squared plus 12x minus 5. So let's start with f prime of x, which would be 3x squared minus 12x plus 12. We're going to set it equal to 0. And if we look at it, we notice that we can factor out a 3. So when we do, we get x squared minus 4x plus 4, which happens to be x minus 2 times x minus 2. So our only zeros here are going to be where x minus 2 equals 0 or where x equals 2. So our only possible extrema will come at x equals 2. So let's look at our f prime of x number line. So if we look at 2, and we're going to test some values around it between negative infinity and 2 and 2 and infinity. Well, between negative infinity and 2, we can test 0. So if we plug 0 into our first derivative, we get 0 minus 0 plus 12. So that's positive. If we test something bigger than 2, like say 3, we're going to get 3 times 3 squared is 27, minus 12 times 3 is 36. So we're at a negative, plus 12, that brings us back up though to a positive. So we have an interesting situation where our function is increasing on both sides of our critical point. So this is where the information from our second derivative is going to be vital to helping us understand what the graph looks like. So let's look at our second derivative, f double prime of x. Well, that's going to be 6x minus 12. And when we set that equal to 0, we find that 6x equals 12, so x is equal to 2. Well, isn't that interesting? Our inflection point and our critical point are the same. So let's see if we can test the same, we'll just test the same values. So at 0, 6 times 0 is 0, minus 12, we get a negative, so concave down. And at 3, when we get 6 times 3 is 18, minus 12 is positive 6, so we get a positive, so concave up. Well, we're not going to have any extrema because even though our second derivative implies a possible max less than 2 and a possible min greater than 2, our increasing and then increasing around the critical point say that can't happen. I don't change directions. So this graph is going to be one of those special ones where when we look at it, we'll see it goes 0 down to negative, starts at 0, negative 5. And at 2, well, when we plug in 2, f of 2 would be 8 minus 24 is negative 16 plus 24 puts us back to 8 minus 5 is 3. Okay, so f of 2 would be 3. So this is at negative 5. So let's see, we've got 2, 3. And it's increasing all the way up to that point, but it's also concave down. So it looks like this. At that point, though, our tangent line becomes 0. So our function has to level off. And then it also is the inflection point, so it also switches to being concave up. So it simply flattens out momentarily here and switches to concave up and continues to increase. For our last example, I wanted to look at what happens when we use first and second derivative rules. So we have this graph, and this came from Pearson, and it has a function, which is the blue, has the function. It has the first derivative, which is the red, and the second derivative, which is the green. And the question says, looking at the graphs of f prime of x and f double prime of x for x close to 10, explain why we have a minimum at x equals 10. Well, you can't just say because the graph has a minimum, right? Let's say we didn't have this graph. Well, we could look at our first derivative and notice that it crosses 0 at x equals 2. So that would be a critical point, which would be a possible max or min. And it crosses again at x equals 10, another critical point, another possible max or min. If we looked at our f prime of x alone, if we looked at 2 and we looked at 10, before 2, our graph of our derivative is above the x-axis, so it's positive. Right? And then if we look at Between 2 and 10, the graph of our first derivative is below the x-axis, so f prime of x itself is negative. So we'll put that on our chart. And then again, from 10 to the end of our graph that we're looking at, theoretically to infinity, or at least to what the window we were given, 10, after 10, it's always positive. F prime of x is always positive. So we'll put that on our chart. So that implies, we can see already then that we've got an increasing, decreasing, increasing. So that certainly implies a max at 2 and a min at 10. Let's see if our second derivative confirms this. I'll find a green color here for you. So let's look at our second derivative. That's this green line. Well, where does it cross the x-axis? Well, that's here at 6. Right? X equals 6 is going to be our inflection point. So if we were to look at the number line for f of x, f double prime of x, we know at 6 it's 0. So let's see what happens when x is less than 6. Our second derivative is below the x-axis, so it is negative and concave down. And then from 6 on, f double prime of x is always above the x-axis, so it would be positive. So it's concave up. This also implies a maximum before 6 and a minimum after 6. So our reasoning here, right, we have at x equals 10, f prime of x equals 0, and f double prime of x at 10 is a positive. So it's positive. So that implies that we have x equals 10 is a relative or local minimum. How could we explain what happened at 2? Well, at 2, by the same reasoning, we could say f prime of 2 is 0, and f double prime at 2 is negative, so f of 2 would be a relative maximum. Both of these agree with the given graph. On the last few slides, I have just summarized in a very long list how you can approach curve sketching. So we start with finding f prime of x, finding all relative extreme points, doing the first and second derivative tests, and then we do the same with our inflection points. So when we do our inflection points, we test those, and then we consider other properties such as the y-intercept, any other x-intercepts, and figuring out where it's defined. And then look for any possible asymptotes and complete your sketch. So you have all of these notes already, so feel free to read through those and make sure that they make sense, especially in regards to the examples that we've done. You may want to read through them and then go back and watch some of the examples again. And so for this week, you need to be working on online homework 9 and quiz number 5. If you have any questions, please feel free to reach out to me.